Hello class, we've been studying about how chemical bonds are formed or broken at a molecular level. We were studying how the valence electrons reorganize themselves during the course of bond formation and bond breakage. We were looking at the how and the why of an organic reaction, that is reaction mechanism. As we have learnt in the previous lecture, bonds can be formed or broken symmetrically or unsymmetrically. So based on this, the most common reaction organic compounds undergo are categorized as radical reactions and polar reactions. The previous lecture focused on the mechanisms of radical reactions. In this and the next lecture, we'll be studying about polar reactions, the mechanisms of polar reactions, the most common reaction among organic compounds. In this 1 hour and 45 minute lecture, we are going to study about nucleophiles and electrophiles, the intermediates of polar reactions. Welcome. So we have now seen the two most common reactions among organic compounds are radical reactions and polar reactions. And polar reactions by far are the most common reactions among organic compounds. It is the most abundant reaction organic compounds undergo, and it is a reaction associated with ions, positively charged cations and negatively charged anions, which are either formed or reacted during the course of unsymmetrical bond formation or cleavage. Polar reactions, however, do not only involve these fully charged species, but they also involve partially positive and partially negative reacting species. So polar reaction involve fully positively charged and fully negatively charged species, cations and anions, but there are also reactions that involve partially positive and partially negative reacting species. So polar reaction is a reaction that involve these oppositely charged species, and then it is based on the principle that opposite charges attract to each other. So the positively charged cations and the negatively charged anions, they attract to each other. The partially positive center of a polarized bond and the partially negative center of a polarized bond attract to each other. It's based on the principle opposite charges attract to each other. It's a principle you've come to be familiar with even when you were young. When you were playing with magnet, you see that when you bring the magnets in a certain direction, they repel each other, but when you bring them in another direction, they attract. Okay, so opposite charges attract and like charges repel. It's a principle based on this. So these oppositely charged species, they can come together, they attract to each other, and then they can come together and form bonds with each other. So there are 4 possible ways in which these oppositely charged species can come close to one another and form a bond. One possibility is when you have a fully negatively charged anion and a fully positively charged cation attracting to each other and forming a bond. The other possibility is when you have a negatively charged anion being attracted to a partially positive center of a polarized bond. The other possibility is when the partially negative center of a polarized bond being attracted to a fully positively charged cation, or when you have two polarized bonds approach to each other, says that the partially negative center of one compound being attracted to the partial positive center of another. So these are the four possible ways in which the reacting species of polar reactions come together, attract to each other to form a bond. So these four type of scenarios arose as a result of the fact that we have ions which are fully positive or fully negatively charged. We also have partially positive and partially negative centers. So if you look at the first scenario, this is a force of attraction between an anion which is negatively charged and a cation which is positively charged. So these ones attract to each other, and then when they come close enough to form a bond, electrons flow from the anion to the cation, in the process forming a bond between them. So there will be a bond that's going to form between Y and X. So as you can see, Y is electron rich, X is electron deficient. Since it is electron deficient, it will be happy if it can get electrons to neutralize this positive charge. Y is reactive because it has got excess of electrons, it is negative. So both of them, they need each other. This one to be neutralized by getting rid of these additional electrons. This one will want to react with something negative so that electrons can come and neutralize the positive charge on it. So when these ones come close to one another, electrons will flow from the electron rich center to the electron poor center. So this we show using a double headed arrow with the direction going from the electron rich center to the electron poor center. So these two electrons will now be used to form a bond between Y and X. So since Y has given its excess electron to form a bond with X, it becomes neutral. Then since X has gained an electron from Y, it also become neutral. Okay, so this one scenario. The other scenario is when you react an anion which is electron rich, which is very highly reactive, you react it with a polar molecule. Say that Y in this case being more electronegative than X, the Y pulls electrons of the bond towards itself. So Y will have excess of electrons, X will have deficiency of electrons. So when this molecule, when this anion approaches this molecule, it will not approach the Y because the Y is negative as the anion is, so they repel each other. But the Y will be attracted to this positive center of this partially polarized bond. So when they come close to one another, there will be a bond that's going to be forming between the Y minus and the partially positive center of this polar bond. The other possibility is this polar bond that has got excess of electrons on B, since it is more electronegative than A. So when this one gets closer to a cation, which is fully positively charged, there is going to be a force of attraction between them. Then electron will flow between B to X, forming a bond between B and X. The other possibility is when you react two different compounds that are involved in polar covalent bond. So this says that now this one is the one that has excess of electrons in this molecule, and then this is the one that has got deficiency of electrons. This is partially negative, this is partially positive. The two attract to each other and form a bond with each other. So these are the four possible ways in which the four reacting species involved in polar reaction react with one another to form a bond. Okay, remember the four are positively charged cations and negatively charged anions, or partially positive center and partially negative species, they react with one another to form a bond. Next, we'll just elaborate on this force of attraction so that you can understand what really attracts the anions and the cations, the partially positive center with the partially negative center. So let us now look at the physical basis for the attractive force that exists between oppositely charged species. Why are cations and anions attracted to each other? Why is a partially positive atom is attracted to a partially negative atom? What are the physical basis of this? Probably some of you might have learned this in your physics studies in high school. If you have two charged species, one of them positively charged, another one which is negatively charged, these two charged species, they can attract to each other. So there's going to be a force of attraction between them. Then the force of attraction that exists between oppositely charged species is governed by the Coulomb's electrostatic force of attraction. And the Coulomb electrostatic force of attraction, that law, Coulomb's law, says the force of attraction that exists between oppositely charged species, Q plus, which is positive, and Q minus, which is negative, the force of attraction that exists between these oppositely charged species is equal to a certain constant K, and then the product of the charges Q, the charge of the positive species, times the charge of the negative species divided by the distance between them square. So what this law is telling us, the force of attraction between two species is directly proportional to the charges. The more charges there are on Q plus and Q minus, the stronger will be the force of attraction. The other factor that determines the force of attraction between them is the distance. The force of attraction is inversely related to the square of the distance. What is telling us, the closer oppositely charged species are to one another, the stronger the force of attraction. Okay, so let's just focus on one thing, that the force of attraction is directly proportional to the charges. The more the charges, the more the attractive force. So let's apply this to our situation, to the partially positive and the fully positive centers, and the partially negative and fully negative ions, and partially positive and partially negative species that are involved in polar reactions. So Q plus, in this case, might represent a positively charged ion, a cation, or a partially positive atom in a polarized bond, which, as we know, are called electrophiles, but we'll learn more about electrophiles in a short while. The Q minus might represent a negatively charged ion, that means an anion, or a partially negative atom in a polarized bond. So the force of attraction that exists between an electrophile and a nucleophile, the strength of the force of attraction is going to be dependent on the magnitude of the charge. So as you can imagine, therefore, the force of attraction between a cation, which is fully positively charged, and an anion, which is fully negatively charged, is the strongest force of attraction that exists in the reacting species involved in polar reaction, because they are fully positively charged or fully negatively charged. The other ones are partial. So the force of attraction between a partially positive center and a partially negative center is going to be weak. So the stronger force of attraction is the one between positive and negative, okay, followed by the one between positive and partially negative center, or positive and negative and partially positive center. So the most important thing is the force of attraction, because for two atoms to form a bond with each other, they must come close to each other. They must attract to each other. So they will come very close to each other. They can form a bond very easily if the charges on these atoms are high. If the bond is very polarized, okay, compared to another bond which is not very polarized, a polarized bond will react very fast compared to an unpolarized bond. Okay, so the principle, we can say that what drives the polar reaction is the Coulombic electrical force of attraction between centers that are fully or partially positive, that means electrophiles, and negatively charged, either fully negatively charged or partially negative centers that exist in functional groups in molecules. Okay, so bond formation will be between one functional group and another functional group. For example, in high school you learned that when you react an alcohol with a carboxylic acid, an alcohol with an acid, you get the sweet smelling ester. For a bond to form between alcohol and the carboxylic acid to form the ester, there must be on one of them a positive center, on the other one there must be a negative center, and then this positive center and negative center on these functional groups attract to each other to form a bond. Okay, so that force of attraction between different functional groups that are involved in making of different types of molecules depend directly on the charges on the reacting species, on the electrophile and the nucleophile. They can be fully positively charged or fully negatively charged, partially positive, partially negative. The partial positive charge on one functional group could be more than the partial positive charge on the other. Okay, so the rate at which they are going to react with one another is going to be dependent on the Coulombic force of attraction. So next we'll study about functional groups, and then how the atoms in a particular functional groups are polarized, so that we can identify in a functional group the electrophilic center as well as the nucleophilic center, so that we can identify the partially positive center and the partially negative center of a functional group, so that we can see the reason, for example, carboxylic acid and alcohol reacting to give us an ester. Which bonds are formed? How are those bonds formed? What really attracted the alcohol to the carboxylic acid in order for it to form a bond with each other, so that this molecule, the sweet smelling molecule ester, is synthesized. So let us now look at the polarity patterns of some of the most common functional group. If you look at a particular functional group, how can you tell which part of this molecule is partially positive and which part of the molecule is partially negative? Because at the end of the day, organic reactions are about the interaction between electron-rich centers, that means the partially negative centers, and electron deficient, meaning the partially positive centers in a functional group. So organic reactions, the most common organic reactions, is about the reaction between nucleophiles and electrophiles. So when you want to understand how a particular organic molecule reacts, you must see and understand how the bonds in this molecule, in this particular functional group, are polarized. Okay, and then knowledge of that will tell us how it's going to react. Okay, so when you have why is it important to know this? Because bond formation is going to be between the electron rich and the electron 4 centers of a functional group, because this oppositely charged species, as we saw, will have this Coulombic force of attraction between them. And then this Coulombic force of attraction is the one which at the end of the day is going to determine how they are going to react, how they are going to form a bond. Okay, so the molecules attract to each other, and then when they reach a certain distance, when they get close to each other, the force of attraction between them becomes very strong, and as a result they end up forming a bond. Okay, so to understand how a bond is formed, how a particular functional group undergoes a chemical reaction, it's very important for us to know the partial positive and the partial negative centers of this functional group. Okay, so when you have a situation where you want to see how one functional group react with another, okay, which atom of this functional group is going to form a bond with which atom of the other functional group, you have to understand the pattern of the polarity of these functional groups. Okay, then if you understand the pattern and identify the electrophilic and the nucleophilic centers in this functional group, you can easily figure out how the bonds are going to form between this different functional group. Okay, so knowledge of understanding of polarity pattern of a bond is very important. Okay, so this we have already discussed, and we know when you have a covalent bond between two atoms, and these two atoms are not the same, these two atoms have different polarities, the most electronegative atom of the two will attract the electrons of the bond towards itself. So on that atom you have excess of electrons, on the other one you have deficiency of electrons. Okay, so understanding the polarity pattern of a chemical bond is not difficult or is not new to you. We have discussed it several times, but now we are applying this principle in determining how organic molecules are going to react with one another. Okay, we use this polarization of a bond to determine the partial positive and the partial negative center, the electrophilic and the nucleophilic centers, so that we can tell how bonds are going to form. Okay, therefore, to understand how a functional group reacts, you must first learn to recognize the electron deficient and electron rich centers in a functional group. So what we are going to see now, we look at different functional group and we see how their bonds are polarized, so that we can determine their partially positive and partially negative centers. So these are some of the most common functional groups you find in organic molecules, and let's look at the polarity patterns of this. Let's identify the electrophilic and the nucleophilic centers in these functional groups. So some of the functional groups we have already covered them. Okay, remember, these are alcohols, these are alkyl halides, these are amines, these are ethers, these are aldehydes, these are ketones, these are carboxylic acid chlorides, esters, and amides. So I have added acid anhydride and thiols and nitriles. Okay, but these are some of the most common functional groups you find among organic compounds. Okay, how are these different bonds, the ones that are indicated, are polarized? First, let's look at this one. Okay, this is an alcohol. So in this, the bond I'm interested in is this one. Okay, the polarized bond between this carbon and oxygen. Okay, because we are going to study the reactions of organic molecules, so our focus will be more on carbon. Okay, how is the carbon in such molecules polarized. Okay, so this is a bond between carbon and oxygen. Then, as you know, oxygen is the second most electronegative element in the periodic table. So as a result of that, this carbon-oxygen bond is polarized. Says that the oxygen being more electronegative than carbon, most of the electrons of this bond will be towards the oxygen. So the oxygen will be partially negative, while the carbon will be partially positive. So this is how that bond is polarized. So the carbon partially negative, the oxygen partially negative. So in an alcohol, the oxygen of the alcohol is partially negative, while the carbon of an alcohol is partially positive. The oxygen of an alcohol is at the nucleophilic center, or the nucleophile of an alcohol, while the carbon of the alcohol is the electrophilic center, or the electrophile. So when you react an alcohol with a reacting species, the reacting species will either react with the carbon or with the oxygen. Whether it's going to react with the carbon or with oxygen, it depends on the nature of this reacting species. If it is negatively charged, it will react with the carbon because opposite charges attract. If it is positive, it will react with the oxygen. So it is very important for us to understand the polarization of a bond, so that we can understand how this particular molecule is going to behave in a chemical reaction. So let's look at the next one. This is a bond between carbon and X, where X is a halogen. As you know, all the halogens, fluorine, chlorine, bromine, iodine, etc., are more electronegative than carbon. So the bond is polarized. On, says that X, the halogen, will have excess of electrons, and the carbon will have deficiency of electron. Okay, so this will be partially negative, this will be partially positive. So this is another bond, an amine, between carbon and nitrogen. So nitrogen is the third most electronegative element in the periodic table. Again, this bond is polarized. So on the nitrogen we'll have excess of electron, on the carbon we'll have deficiency of electron. So amines generally are very strong nucleophiles. The reason why they are strong nucleophiles, because on the nitrogen of amines we have this partially negative charge. This partially negative charge is very high because this bond is very polarized. Most of the electrons of this bond are on the nitrogen. Okay, so the Q minus, very high. Okay, so that's why it can easily attack as a nucleophile, react with something that is electrophilic. So let's look at this carbon-sulfur bond. Again, the carbon-sulfur bond is reasonably polarized. Sulfur is a bit more electronegative than carbon. So on the carbon, we have partially negative charge. On the sulfur, we have a partially negative charge. So let's look at this example. This is unlike this one, which is a single bond. This is a triple bond. As you know, a triple bond is made of a sigma bond and 2 pi bonds. Okay, and so let's look at the bond first. So the carbon and the nitrogen is more electronegative than the carbon, so there will be excess of electrons on the nitrogen and deficiency of electrons on the carbon. So partially positive charge on the carbon, partially negative charge on the nitrogen. So in here we have in total 6 electrons. Okay, the 3 bonds. Okay, so the 6 electrons of this bond are attracted, most of these electrons are attracted to the nitrogen. So on the nitrogen we'll have a partially negative charge, on the carbon we'll have partially positive. So in a nitrile, this nitrogen will be very nucleophilic, and then this carbon will also be very electrophilic. The more negative this is, the more positive the other one is. Okay, because as this one take away electrons to enrich itself, this one is losing electrons. Okay, so the more electron rich this one becomes, the more electron deficient this one becomes. So in terms of magnitude, sigma plus these charges are the same. This sigma and these partial charges are the same in terms of magnitude. Okay, so let's look at this one. This is an ether, and in an ether you have an oxygen flanked by 2 carbons. Okay, so oxygen is more electronegative than carbon, so this oxygen will take away electron from this carbon. The same oxygen will also take away electron from this carbon. All the same, the oxygen will be partially negative while the carbons become partially positive. So this is the polarization pattern of an ether. I want you to see, if you were to compare the partial positive charge on, in terms of magnitude, the partial positive charge on an ether and the partial charge on an alcohol, this partial positive charge and this partial positive charge, which of these partially positive charge are more positive in terms of magnitude? Which charge is more? Is it the positive charge on the carbon of an alcohol, or is it the positive charge on the carbon of an ether? What do you think? See here, this oxygen is involved through one bond with this carbon. Okay, so this oxygen will use all its resources to pull electrons from this carbon. Okay, so it becomes very negative, the other one becomes very positive. But in this case, this oxygen, it's the same oxygen, but in this case it has to pull electrons from both sides. It is power, it is power to attract the electrons of this sigma bond. The single bond is divided into 2, so it will not be as strongly attractive as in the case of the alcohol. So the partial positive charge on these will be less than the partial positive charge on a carbon, or the partial negative charge on oxygen of an ether will be less than the partial negative charge on an alcohol. So in terms of reactivity, if you compare the nucleophilicity of the oxygen of an ether and the nucleophilicity of the oxygen of an alcohol, you will find the oxygen of an alcohol is more nucleophilic than the oxygen of an ether. Okay, so let's go to this one. Okay, so in this case, in all these cases, in all these examples, this is an aldehyde, ketone, carboxylic acid, acid chloride, an ester, acid anhydride, and amide. In all this, what is common is we have a carbon oxygen double bond, carbon oxygen double bond. Okay, so these bonds are made of sigma bond and pi bond. Okay, so let's focus on the basic thing first. So in here you see, since oxygen is more electronegative than carbon, the oxygen will pull electrons of this bond towards itself. So on the oxygen you should expect to see excess of electrons. On the carbon you should see deficiency of electrons. So this will be partially positive, while this one will be partially negative. Okay, this is partially positive and this is partially negative. Again, let me ask you, which carbon is more electrophilic? The carbon of a carbonyl or the carbon of an alcohol? Which carbon is more positive? Is it this one or this one? Or in other words, which oxygen is more negative? Is it the oxygen of a carbonyl or the oxygen of an alcohol? I want you to see this. Here we have 2 bonds. Okay, in these bonds we have 4 electrons. This one only have 2 electrons. This bond, so in both the carbonyl compound, in both this one and the alcohol, we have a sigma bond. Okay, that is constant. But this one has got an additional bond, a pi bond. And then you remember, electrons of a pi bond are loosely held by the nucleus. So this oxygen will attract the electrons of, in addition to attracting the electrons of the sigma bond towards itself, it will also attract the electrons of the pi bond. And the electrons of the pi bond, since they are loosely held by the nucleus, they can easily be attracted to the other side. So as a result, carbonyl compounds like aldehydes are more electrophilic than alcohols. This one can easily be attacked by a nucleophile. You remember a nucleophile is either either partially negative or fully negative, which can be attracted to this. So if you compare the electrophilicity of carbonyl carbon and the carbon of an alcohol, the carbon of carbonyl compounds like aldehydes are more electrophilic. Okay, so it's the same case for ketones. Okay, these ones are also very electrophilic. The partial positive charge in these are more than the partial positive charge in here. Partial positive charge in here, the partial positive charge in here, the partial positive charge in here. Because in addition to the sigma bond, they have a pi bond. And pi bonds are easily polarizable. They can easily be taken to one side because pi bonds, as you know, are formed through sideways overlap of p orbitals. So the nucleus does not have strong force of attraction for these pi bonds. Okay, so they can easily be taken away, taken to one side. So these are very electrophilic. Because these ones, the oxygens are very nucleophilic, and the carbonyl carbons are very electrophilic. As you shall see later, a nucleophile easily attack the carbonyl carbon of carbonyl compounds. So the reaction of carbonyl compounds is dominated by the fact that these carbonyl carbons are very electrophilic, and the nucleophile comes and attacks them. Okay, so let's look at carboxylic acid. Again, this is a bond between carbon and oxygen. So you have this situation. Okay, now in here we have two oxygens. Okay, this oxygen and this oxygen. Which oxygen do you think is more negative? Is this oxygen the one involved in a double bond, or is it the oxygen that is involved in a sigma bond? Which one do you think is more negative? Again, very easy to see. This one has got only one bond, sigma bond, which are strongly held. But this one also has got a sigma bond, but in addition, it has got a pi bond. Okay, so as a result, both the electrons of the sigma bond and the pi bond are on this oxygen. Okay, so as a result, I even put in terms of magnitude, I made this partially negative charge more than this. Okay, so this oxygen is more nucleophilic than this. So if you were to react a carboxylic acid with an electrophile, most probably, without any doubt, the electrophile will react with this oxygen and not with this one. Okay, so another one is acid chlorides. So we have this acid chloride, we have a carbon oxygen double bond, and then a chlorine. Okay, so again, this is polarized like that. The same is to esters, the same is to acid anhydrides. Okay, and the same is to amides. So you will learn more about these things later. Okay, those of you will continue with organic chemistry, you will learn more about the reactions of such type of compounds, nitriles, all the carbonyl compounds into O6. Okay, but I want us I want us to know what the polarization pattern of such molecules are, which we can easily tell based on the chemistry we have learnt so far. Is it okay? So these are how bonds are polarized. So when you want to see, when you want to figure out a reaction between two functional groups, you have to know the polarization pattern between what the polarization pattern of these functional groups are, so that you can identify the electrophilic centers and the nucleophilic centers in each functional groups, so that you can easily say, so when this functional group and this functional group react, so this electrophilic center on this functional group will react with the nucleophilic center of this, and then you form a bond. For example, you remember in high school you learned that when you react a carboxylic acid and an alcohol, you form an ester. How is a carboxylic acid? This one is going to react with an alcohol. Go. So the way it's going to happen, after the ester is formed, okay, when you want to figure out the reaction mechanism, of course, you have to know what the product of the carboxylic acid, what the result of the reaction between this and this one is, okay. The reaction of this with this, it's an ester, okay. So when you look at this, this an ester, this part of the ester is from an alcohol, while this part of the ester is from the carboxylic acid. So at the end of the day, there is a bond that is formed between this oxygen and that carbon, between this oxygen of an alcohol and this carbon of the carboxylic acid, okay. So you can easily tell the bond must have been between the alcohol as a nucleophile through its oxygen and the carboxylic acid as an electrophile through this carbonyl carbon. So there is going to be a reaction between this one and this one, because this is negative, this one is positive. They attract to each other and forming a bond, okay. So understanding the polarization pattern of a bond is very important, okay. If you know, without even knowing what, for example, what happens when you react an amine with a carbonyl, for example, you can easily start writing what the product are, because you'll see in an amine you have this nitrogen, which is nucleophilic, very nucleophilic. In a carbonyl compound like ketone, this carbon is electrophilic, so you should expect this nitrogen and this carbonyl carbon, since they are oppositely charged, okay, to attract with one another, and then you can easily start the reaction by forming a bond between this nitrogen and this carbon, okay. So recognizing the polarity pattern of functional group is very, very important, okay. So these are polarity patterns of the most common functional groups, okay. I know there could be some other functional group which I may not have put in here, but when you look at any of this bond, you should be able to tell how the bond is polarized, okay. So identifying electrophilic and nucleophilic centers in a functional group is fundamental, is very, very important, because bond formation in polar reaction is between these sides. So when you see a reaction between two molecules, you have to know the electrophilic and the nucleophilic centers in these functional groups, okay. Then once you figure out, you can see which bond is going to be formed. The bond will certainly form between the electrophilic center of one and the nucleophilic center of the other. So it's very, very important. I've said a lot of things about electrophiles and nucleophiles, really without really explaining to you what they are really about. So we are going to study next electrophiles and nucleophiles. What are electrophiles and what are nucleophiles? How can you identify an electrophile? How can you identify a nucleophile? Because at the end of the day, chemical reaction is going to be between electrophiles and nucleophiles, isn't it? So you must know and identify electrophiles and nucleophiles, okay? So we're going to learn first basic definition of an electrophile and a nucleophile, okay? So let me now define the terms electrophiles and nucleophiles, which I have mentioned severally since we started talking about reaction mechanisms, okay? So in order for us to understand the basic definition of this, I have split these words into two. Okay, so the one in blue and the other one in red. Blue and red. The blue part is very clear. Electro means electron, while nucleo means nucleus. What is this word files that has modified electron or nucleus mean? Okay, so let's look at it. So the word files or philic, it denotes a person or a thing having love for a specified thing. Okay, so this philic or file is associated with love. Okay, you remember, in addition to the terms electrophiles and nucleophiles, I was also using a modified term of this, electrophilic and nucleophilic. So the word files and philic are basically the same. They are associated with a person or a thing having a love for a specified thing. So it's associated with love. Okay, electrophile, nucleophile, those that love electrons and those that love the nucleus. Okay, so for us to better understand these words philis and philic, let me give you the opposite, the antonym of this word files or philic, which is phobia, and which, as you know, phobia is extreme, unjustifiable fear or hatred for something. Phobia is associated with extreme hate. Okay, so the opposite term, philic or files, is associated with extreme love. Okay, so let me just break it down. So now we have electrophiles and nucleophiles. Then what do you think this term electrophile means? Those that love electrons. How about this term nucleophile? For sure it means those that love the nucleus. So electrophiles are electron loving, while nucleophiles are nucleus loving. So these are lovers of electrons, these are lovers of the nucleus. Okay, so remember, phobia and phil are opposite. So these are those that love electrons extremely, while these ones are those that love the nucleus extremely. Okay, so electrophiles are lovers of electrons, while nucleophiles are lover of nucleus. Okay, this may not be very straightforward. Let me look at this first. Okay, so lover of electrons. What are electrons? What is the charge of electrons? Electrons are negatively charged. Okay, therefore electrophiles are those that love negative charge. Okay, those ones are called electrophiles. How about nucleophiles? It is not very straightforward the way it is defined, but if you look at the nucleus, what is the charge of the nucleus? The charge of the nucleus is positive. Okay, so nucleophiles are those that love positive charge. Okay, so that's how they are defined. Electrophiles, they are lovers of negative centers. Since why they are, because they love electrons, because why they are defined as such is because electrons are negatively charged, so they love negative centers, which is a charge of electrons. Whereas nucleophiles, they love positive centers. Since they love, since the charge of the nucleus is positive, so nucleophiles are those that love positive centers. Okay, so electrophiles love either something that is fully negatively charged or partially negative, while nucleophiles love something that's either fully positively charged or partially negatively charged. Okay, so electrophiles, since they must, because since opposite charges attract, okay, so electrophiles, since they love electrons, they must have the opposite charge. So electrophiles are positively charged. Nucleophiles, they love positive centers. So nucleophiles, they must be negatively charged. They can be fully negatively charged or partially negatively charged, whichever the case, negatively charged. Electrophiles, they can be partially positive or fully positively charged, all the same, positive. So electrophiles are positively charged. Okay, this positive charge, it can be fully positively charged, as in the case of cations, or they can be partially positive, as in the case of the partial positive atom of a polarized bond. Okay, or nucleophiles are negatively charged. Okay, they can be fully negatively charged, as in the case of an anion, or they can be partially negative, as in the case of the negative atom, the partially negative atom of a polarized bond. Okay, so electrophiles and nucleophiles have opposite charges. Okay, since they have opposite charges, they love one another. Okay, so electrophiles, they love nucleophiles. Nucleophiles, they love they have extreme love for each other. Okay, that's why nucleophiles and electrophiles attract one another in a polar reaction to form a bond. Okay, so electrophiles by definition are those centers that are electron deficient. They are electron deficient, while nucleophiles are electron rich. So electron rich and then electron deficient centers attract to one another. Okay, so electron deficient, it could be fully positive or partially positive, whichever the case, electron deficient. While electron rich, it can have a full negative charge, making it very rich, or a partially negative charge, making it reasonably electron rich. Okay, so at the end of the day, electrophiles and nucleophiles, they love one another. Okay, that's what is the basis of the reaction between nucleophiles and electrophiles that results in bond formation in polar reaction, the most common, the most abundant reaction in organic molecules. Okay, so most chemical bonds in organic compounds are formed as a result of bond formation between nucleophiles and electrophiles. Nucleophiles and electrophiles, they form a bond with each other, as you know, because they are oppositely charged, and they have this Coulombic force of attraction between them. They come very close to each other because of that attractive force. When they reach a certain distance between each other, the force of attraction becomes very strong. As a result, they form a bond. So these are the basic definition of electrophiles and nucleophiles. So next, we are going to see ways of identifying an electrophile and a nucleophile. How electrophiles and nucleophiles react with one another. That's what we are going to study next. So with this basic definition of electrophiles and nucleophiles, now we have understood what electrophiles and nucleophiles are. Let me further break down what electrophiles and nucleophiles are, how they undergo reaction, how we can recognize an electrophile. Electrophile are those that love electrons. So since they love electrons, they must be positive. So an electrophile can be fully or partially positive. Those that are fully positively charged are called cations, and those that are partially positive, these are the ones that result from polarized bond. The partially positive of a polarized bond can be an electrophile or a cation, one that is fully positive. In an abbreviated form, electrophiles are represented using the letter E. Okay, when you say E+, we are talking about an electrophile that is fully positively charged. So if it is a carbon that is fully positively charged, which, as we'll learn, carbon that is fully positively charged is called carbocation. Okay, it's a cation, but since it's a carbon cation, it is called carbocation. Okay, so electrophiles, they can be fully positively charged or partially positively charged. Okay, so those are the two types of electrophiles. So as a result, when they are partially positive, the electrophiles are neutral. When they are fully positive, the electrophiles are positively charged. So we have two types of electrophiles. Okay, one that is fully positively charged, but another one that is partially positive. In order for it to be partially positive, the atom to which it is connected to must be partially negative. So the partially positive and the partially negative cancel out each other. At the end of the day, the molecule becomes neutral. So we have two types of electrophiles, neutral and positively charged. Okay, so we have two groups of electrophiles, neutral electrophiles and positively charged electrophiles. Okay, so let's look at each of them, the categories that exist in them, and so that you can identify an electrophile very easily. So let's first look at the neutral electrophiles. Okay, so these are the type of neutral electrophiles. So why they are neutral? As you can see, this carbon is partially positive because the nitrogen pulled electrons away from the bond. In the process, the nitrogen became partially negative. So this is partially negative. This is equally partially positive. The two charges cancel out. So this is neutral, but it has got a carbon which is partially positive. So this carbon is an electrophilic carbon. The same in a carbonyl. Okay, so this carbon is electrophilic. The same in halogen. So this carbon is electrophilic. These are neutral electrophiles. So these neutral electrophiles, these are electrophilic carbons that resulted as a result of a polarized bond. As a result, this carbon is electron deficient. This one is also electron deficient. This one is also electron deficient. You can clearly see this one has got a partially positive charge. This one has got a partially positive charge, the same as to this one. Okay, these are neutral with electrophilic or electron deficient carbons. The other category of neutral electrophiles that do not have partial charges are these ones with an incomplete octet. You remember when we were studying about Lewis structures, we saw exceptions to the octet rule. Those atoms that have less than octet of electrons and those that have more than octet of electrons. Compounds of elements of period 3 of the periodic table, boron and aluminum, for example, such type of molecules, they have an incomplete octet. For example, if you look at boron, on boron we have only 6 electrons. On the aluminum, the same way, we have through the 3 sigma bonds, we have 6 electrons. This has got only 6 electrons. Boron has also got 6 electrons. These are neutral compounds. But you remember I told you, despite the fact that these are neutral, they are very highly reactive. The reason why they are reactive is because they do not have octet of electrons. So despite the fact that these are neutral, you don't even see polarization of a bond. The boron and aluminum in here are electrophilic because they have an empty orbital. They will want to add electrons so that they can have octet of electrons like the other elements in the periodic table. Okay, so as a result, boron and aluminum trichloride are electrophiles. They are neutral. They don't have a partial positive or a partially negative center. Why they are electrophiles is because they have an incomplete octet. They will want to have octet of electrons. So they will react with a nucleophile that can bring in 2 electrons. Okay, 2 electrons so that they can have octet. So these are the 2 categories of neutral electrophiles. Okay, electrophiles, you should be able to recognize them very easily. Okay, among the neutral electrophiles, we have those that have a polarized bond. Okay, in this polarized bond, the partial positive centers, these ones are electrophiles. And then in those compounds that have an incomplete octet, aluminum and boron, the ones that are indicated in red, these ones are neutral electrophiles. Okay, the other ones are, of course, positively charged electrophiles. So there are two types of electrophiles, neutral and positively charged. The neutral ones are those that have polarized bond, and those that have incomplete octet. The positive ones, of course, any carbon or atom that has got a full positive charge is an electrophile. Okay, so it can be a carbocation. Remember what I told you, a cation is something that is fully positively charged. Okay, and then carbocations are cations of carbon. So when you have a carbon that has got deficiency of electrons, so if you look at this carbon, it has got only 3 bonds. Okay, 1, 2, 3, 4, 5, 6, only 6 electrons, not octet of electrons. Okay, it has got, its normal carbon normally forms 4 bonds in order to have 8. Okay, but this one has got less, so as a result, this is fully positively charged. Another fully positively charged electrophile is an acid, H+. Okay, another very common example of an electrophile, which if you continue with organic chemistry, you'll study more about, is the nitro group. On the nitro functional group, on the nitro group, the nitrogen is positively charged. So this one reacts with a nucleophile. So electrophiles, since they are electron deficient, since they are electron poor, they react with nucleophiles. So what does a nucleophile do to an electrophile? It donates electrons to an electrophile so that this electrophile can have octet of electrons. So an electrophile, in order to have octet of electrons, therefore forms a bond with a nucleophile by accepting a pair of electrons from a nucleophile. Okay, so an electrophile by definition is one that has a species, a reacting species that has extreme love for electrons. Okay, so they seek a pair of electrons. So let me discuss about nucleophiles similarly. So as the name implies, nucleophiles are those that love the nucleus. Remember, the nucleus is positively charged, so as a result, nucleophiles are those that love to react with something that is positively charged. So as a result, nucleophiles must be negatively charged. They can be fully negatively charged or partially negatively charged. Okay, so those that are fully negatively charged are called anions, and those that are from a neutral bond, in a polarized bond, the partially negative atom of a polarized bond can act as a nucleophile. So the simple abbreviation for nucleophiles is Nu. So the nucleophile can be, when it's negatively charged, it is given as Nu minus, while the neutral is treated as Nu. Remember, I told you when we were talking about electrophiles, I told you a positively charged carbon is called carbocation. Similarly, a negatively charged carbon, a carbon that has got an excess of electrons, a carbon that is negatively charged, is called carbanion. So nucleophiles are those that have negative charge. They can be negatively charged or they can be neutral. As a result, nucleophiles can be either neutral or negatively charged. So we can divide nucleophiles into these two groups as neutral nucleophiles and negatively charged nucleophiles. Okay, so a negatively charged nucleophile is very straightforward. The nucleophile, it could be a carbon, it could be an oxygen, or it could be a nitrogen. It is negatively charged. So because it has got excess of electrons, it is for sure a nucleophile. So the neutral nucleophiles are divided into two groups, those that have lone pair of electrons. Okay, so we said a nucleophile is electron donating. Okay, it donates electrons. For it to donate electrons, it must have electrons. So these electrons a nucleophile donates and forms a bond with an electrophile with are usually in the form of lone pair of electrons. Okay, so if you look at water, on water we have oxygen that has got two lone pair of electrons. In an alcohol we have oxygen that has got two lone pair of electrons. In an amine we have this nitrogen that has one pair of electrons. It is these electrons that these nucleophiles are going to donate to form a bond with an electrophile. Of course, when you look at these bonds, even though I have not indicated them as partially positive and partially negative, you should recognize that on these oxygens in the water and alcohol, as well as on the nitrogen, there is a partially negative charge. So because these bonds are polarized, this is a bond between hydrogen and oxygen. Oxygen is more polar than hydrogen, so the oxygen will pull away electrons of this bond. Okay, so on the oxygen we'll have a partial negative charge, on the hydrogen you have a partial positive charge. Okay, so these are neutral nucleophiles. Okay, so the reason why they are nucleophiles is not only because the bond is polarized, but they also have lone pair of electrons which they can donate. Okay, so neutral nucleophiles can be those that have lone pair of electrons that are easily accessible, that can easily be donated to an electrophile. But the other type of neutral nucleophiles are those that do not have lone pair of electrons, but they have electrons which are accessible. An example of these are electrons in a pi bond. Okay, so if you have a double bond or a triple bond, in these double bonds and triple bonds we have pi bonds. Okay, in a double bond we have one pi bond, in a triple bond we have two pi bonds, and these pi bonds are accessible. They can easily be donated. You remember in an alkene, for example, when the hybridization of the carbons, these carbons are sp2 hybridized. So in this alkene we have a sigma bond which is formed by a direct head-on overlap of sp2 hybridized orbitals, but we also have a pi bond which is formed by sideways overlap. Okay, so this is a pi bond. Then as you can see, the sigma bonds are locked between the atoms. They are not easily accessible, but the pi bonds are very easily accessible. So a pi bond can easily be donated to an electrophile, and so that's why alkenes, they undergo a chemical reaction with electrophiles by donating their electrons that are involved in pi bond. Okay, so we remember in here, between the two atoms of the alkene we have 4 electrons. Okay, in the case of alkanes we only have 2 electrons between the two atoms. Okay, first, these electrons are involved in sigma bond. Okay, sigma bonds are very strong. Further, the electrons of the sigma bond are found locked between the two nuclei, so they are not easily accessible. But in the case of an alkene, it has got 4 electrons. It is more electron rich compared to alkanes. Okay, further, its pi bonds are very easily accessible. That's why alkenes are very highly reactive. Alkenes behave like nucleophile. Okay, the same is true for alkynes. Okay, alkynes they have 2 pi bonds which are easily accessible. They can easily form a bond with an electrophile. So when a pi bond, for example an alkene, forms a bond with an electrophile, these pi bonds break, and then the electrons of this pi bond, they are the ones that are going to be used to form a bond with the electrophile, which is electron deficient. Remember, electrophiles are electron pair acceptors. Since they are electron deficient, they accept a pair of electrons. So those pair of electrons which an electrophile will accept from an alkene comes from the breaking of the weak pi bond. So this pi bond breaks, and then the electrons that will be used to form a bond with the electrophile. In the case of neutral nucleophiles, it is electrons that are in the lone pair of electrons. They are the ones that are going to be used to form a bond with an electrophile. For example, if you take nitrogen in amines, it has got this lone pair. So this lone pair of electron will be used to form a bond with an electrophile. So in the process, these electrons, these are the ones that were only on the nitrogen, now will be used to form a bond with an they will be shared between the nitrogen and the electrophilic atom. Okay, in the case of water and alcohol, these ones have 2 lone pair of electrons. Okay, so one of the lone pair of electron will be used to form a bond. Okay, so in the process, this one loses one of its lone pair of electron. It loses it, and it will be used to form a bond with another element. Okay, nucleophiles, they behave as electron donating species because they have electrons. The electrons in nucleophiles, they are found either as lone pair of electrons, okay, in these species, or as a pi bond. So these pi bonds, as well as a lone pair of electrons, have allowed a nucleophile to behave like one that donates electron. So nucleophiles, they donate electrons because they have easily accessible electrons. These easily accessible electrons, they can be in the form of lone pair of electrons, or they can be in the form of a pi bond. Okay, so these are neutral nucleophiles. Of course, it's easy to recognize negatively charged nucleophiles. Okay? So those that are negatively charged. Okay, so if you have water, for example, if you take away this hydrogen, okay, with a base, you get hydroxide. Okay, the difference between a hydroxide and water is neutral, hydroxide is negatively charged. Since this is neutral and this is negatively charged, of course you expect this one to be very aggressively reactive. Further, this has got only 2 lone pair of electrons. This has got only 4 electrons, while this one has got 6 electrons. So if you compare a negatively charged nucleophile and a neutral nucleophile, of course you expect the negatively charged nucleophile to be very highly reactive. So you can have hydroxides, you can also have alkoxide. Alkoxide are those that are derived from alcohols. When you bring a base and take away this hydrogen, you create an alkoxide. Alkoxide is negatively charged. It has got 6 electrons, unlike 4 electrons in alcohol. So alkoxide are very highly reactive. Okay, and then carbon ions, a carbon that is fully negatively charged. It can also work for amines that are negatively charged. Okay, so these are negatively charged nucleophiles. Again, why they are nucleophiles is because they have lone pair of electrons which they can donate. So in terms of reactivity between the negatively charged and the neutral nucleophiles, you should expect the negatively charged nucleophiles to be very highly reactive. So if you have a reaction that introduces an OH into a bond, it is very easy to introduce that OH bond into a particular bond if it is reacted with a hydroxide than with water, because hydroxide, this hydroxyl group, is very highly reactive. One, why it is reactive is because it is charged, okay? The fact that it is negatively charged, it is highly reactive. Further, of course, it is more electron rich. Water is not highly reactive. Alcohol is also not very highly reactive, despite the fact that they have two lone pair of electrons. Despite the fact that they are in a polarized bond, these are not very strong nucleophiles. So if you want to convert water or an alcohol to a strong nucleophile, you bring a base and take away these hydrogens, okay? When you take away this hydrogen, the water will be converted into hydroxide, the alcohol will be converted into an alkoxide, and when that happens, the reaction goes very fast. It's okay? So these are what we call nucleophiles. Okay, you should be able to recognize a nucleophile as well as an electrophile. Remember, the electrophiles, they can be neutral or positively charged. Again, the positively charged electrophiles are going to be very highly reactive compared to the neutral electrophiles. A nucleophile, since it has got these electrons, it wants to donate. Okay, it donates these electrons to an electrophile, and it forms a bond with an electrophile by donating its electrons. So what we did so far is to recognize whether a reacting species is a nucleophile or an electrophile. So by looking at a particular molecule, we should be able to identify whether it is going to act or react as a nucleophile or as an electrophile. Okay? Electrophiles are electron deficient. They either have a full positive charge or a partial positive charge. Nucleophiles are either fully negatively charged or partially negatively charged. They have excess of electrons to donate to something that needs electron, to an electrophile. Okay, so a nucleophile donates its electrons. The electrons in a nucleophile can be lone pair of electrons or electrons that are involved in pi bond. Is this okay? So a nucleophile, as I said, forms a bond with an electrophile by donating its pair of electrons. So the same, it is possible, the same molecule can be a nucleophile and an electrophile at the same time. Okay, so that's what we are going to discuss next, that there are molecules that can behave as electrophiles as well as nucleophiles. Whether they are going to behave in a particular situation as an electrophile or as a nucleophile will depend on the reaction condition. Just implied that some molecules can behave at the same time as a nucleophile or an electrophile at the same time. They can have dual properties, dual behavior as an electrophile and as a nucleophile at the same time. This is particularly the case when the molecule is neutral. A neutral compound that has got a polarized bond. For example, if you take this molecule, then if you look at, if you isolate this bond, the carbon-oxygen bond, this bond is polarized. Since oxygen is more electronegative than carbon, so the electrons of this bond are on the oxygen. So the oxygen is partially negative while the carbon is partially positive. Okay, it is polarized like that. So as you can imagine, so in the same molecule we have two polarized atoms. Okay, so the oxygen is partially negative while the carbon is partially positive. Okay, so this can act as an electrophilic center while this one can act as a nucleophilic center. So this compound has got dual properties. It can react as an electrophile or it can react as a nucleophile. Okay, So this is an electrophilic carbon, while this one is an nucleophilic oxygen in the same molecule. Okay, it's okay. So this does not happen for charged species. Okay, either it cannot happen for an electrophile that is positively charged or a nucleophile that is negatively charged. It happens to neutral molecules that have a polarized bond like this. Of course, the bond is polarized. Since the bond is polarized, one of the centers will be partially negative, the other center will be partially positive. The one that is partially positive will be an electrophilic center, while the one that is partially negative will be a nucleophilic center. These molecules, such type of molecules, they have dual properties. They will behave as electrophilic species or nucleophilic species depending on the reaction. Okay, so depending on the circumstances, such type of compounds can behave either if you react this molecule with a nucleophile. Okay, a nucleophile. Remember, a nucleophile is electron rich. It wants to react with something that is electron poor. So if you react this molecule, if you subject this molecule, if you force this molecule, if you make this molecule to react with a nucleophile, of course it's not going to behave as a nucleophile. Okay, because the nucleophile will come to this side, it will be repelled. The only way the nucleophile is going to react with this is through its electrophilic carbon. So when this one reacts with a nucleophile, it behaves like an electrophile. Okay, however, when you react this molecule with an electrophile, the electrophile is not going to react with this. The electrophile is going to react using the partially negative center of this molecule. So this molecule is going to behave like a nucleophile. Okay, so depending on the reaction condition, neutral molecules that have a polarized bond can behave as a nucleophile or an electrophile. Okay, so in the same molecule you can find electrophilic center and nucleophilic center. So we learned about nucleophiles and electrophiles from the very basic definition. Okay, you know what electrophiles are, you know what nucleophiles are. You've also understood what the basic structure requirement for a reacting species to be a nucleophile or an electrophile. Okay, so and we also learned in this the last slide that the fact that neutral molecules that have a polarized bond can have dual properties. They can behave as nucleophiles or electrophiles. How they are going to behave in a particular situation will depend on the nature of the reaction. Okay, so let me summarize what we've learned so far. A polar reaction is a reaction that involves fully or partially charged reacting species that have opposite charges. The force of attraction that results in bond formation between these oppositely charged species is governed by simple laws of nature. Opposite charges attract. So when these opposite charges attract, they will be attracting to each other based on the Coulomb's electrostatic force of attraction. So this force of attraction that exists between them first depends on the charges. The other factor that determines the force of attraction between these reacting species is the distance between them. So the closer these oppositely charged species that attract to each other, the closer they are, the stronger will be the force of attraction. So they attract to each other, and then as they get very close to one another, the force of attraction will be very strong. At the end of the day, they will end up forming a bond. Okay. So the bond that they are going to form will be as a result of electrons. Remember, a bond is formed between two atoms. What hold one atom with the other one is electrons. So when this nucleophile and electrophile attract to each other, when they come close to one another, and then when they form a bond, they will be forming a bond as a result of electrons. So electrons that are going to be used for bond formation between the two atoms, between the nucleophile and the electrophile, will be supplied by the nucleophile. The nucleophile is electron rich. It has got electrons either as lone pairs or electrons in a pi bond, which it can donate to an electrophile to form a bond with it. Okay, so electrons are going to move from the nucleophile to the electrophile. Then as you know, we show the movement of electrons from an electron rich center to an electron poor center using an arrow. In this case, we use a curved arrow. Okay, so before we go to discuss about reaction mechanisms with examples, let me once and for all discuss about the precise meaning of these curved arrows. They must be used precisely. Okay, so let me just revise what we've learned so far about curved arrows. So let me once again talk about the curved arrow, which we use to show the movement of electrons when we are describing the mechanism of an organic reaction. When we are describing how a chemical reaction, an organic reaction, happen at a molecular level by showing movement of electrons. First, the arrow we use to show the movement of electrons are curved arrows. They are not straight arrows. Straight arrows are used for some other purpose. For example, you remember, you can have a straight arrow that points in one direction. This is what we use to show an irreversible chemical reaction. A going to give a product, B not going back to give product, an irreversible reaction. We also use as straight arrows that point, one pointing to the forward direction, another one pointing to the backward direction. We use that to show a reversible reaction. A goes initially, A molecules react under a particular reaction condition, give product B, and then the sooner B molecules are formed, they go back to give product A, a reaction that goes in both directions, a reversible reaction. We use two arrows, one pointing to the forward direction, other pointing to the other direction. Okay, so the arrows we use in chemistry, in organic chemistry, have precise meaning. So the arrow which we use to show the movement of electrons in a chemical reaction, be it a polar reaction or a radical reactions, are curved. Okay, so this is a curved arrow. We don't use straight arrows, otherwise it will lose the meaning. There will be confusion. So to avoid confusion, we use a curved arrow. So in this particular case, for polar reaction, the curved arrow we use is a double-sided arrow. Okay, so these curved arrows we use in organic chemistry have very precise meaning. Okay, so curved arrows have very precise meaning, and they must be drawn precisely. Okay, we are going to, if you are continuing with chemistry, with organic chemistry, you are going to use arrows and arrows. Organic chemistry is all about arrows, about curved arrows. So you must know how to use them precisely so that you can communicate the right message. Okay, so this arrow that is double-sided, it is used to show the movement of two electrons. Okay, so this is a double-sided arrow. It has got two. This arrow is two-sided. Okay, double-sided arrow. This arrow shows the movement of two electrons. If you are interested in showing the movement of one electron, we'll have a fishhook arrow or an arrow that is only one-sided. So since this is a movement of two electrons in a polar reaction, we have to use a double-sided arrow. That's one. And then this arrow, as you can see, it has got a tail and a head. Okay, what we place at the tail end of this arrow and then at the head end of this arrow are precise. Okay, so at the tail of the arrow we put the nucleophile. That's where we have the nucleophile. End of the arrow we have electrophile. So the source of the electrons, the nucleophile, will be at the tail, and then the arrow will move from the nucleophile towards the electrophile and not the other way. Okay, so the nucleophile is, so the tail of this curved arrow is placed on the nucleophilic center, and its head is pointing or is placed on the electrophilic center, not the other way. It is where you put the electron donor. The nucleophile is the one that donates electrons. You put the electron donor at the tail, while the electron acceptor, you put it at the head. The electrophile will be at the head, not the other way. See, this one is electron rich. This one is electron poor. Assume this one is a rich person, this one is a poor person. Okay, what happens normally? The rich give to the poor. The rich gives, okay, and the poor accepts. That is the natural order of things, from the haves to the have-nots, from the electron rich nucleophile to the electron poor electrophile, and not the other way. It is not a situation where the poor go and rob the rich and take their possession. That is robbery with violence, which is not acceptable. So when these arrows are drawn, they should be drawn from the source of the electrons, from the electron donor to where the electrons are required, to the electron acceptor, from the electron source to the electron destination. The tail will be at the source of the electrons, while the head will be at the destination of the electrons and not the other way. Okay, so the nucleophile, this electron rich, the one that donates electrons to the electrophile, this ability to donate electrons is because it has got electrons. These electrons it has, they can be in the form of lone pair of electrons, as in the case of a negatively charged nucleophile or a partially negative nucleophile, okay, in a neutral polarized bond. So these are lone pair of electrons. The other form of electrons which a nucleophile donates to an electrophile, these are electrons that are in pi bond. So if you have a pi bond between two identical elements, so if you have a pi bond between two carbons, okay, such type of electrons that are involved in such type of pi bonds can be donated. Okay, so while the electron acceptor is electron deficient. The reason why it's electron deficient, it is because it is lacking electrons, and this can be in the form of a reacting species that is positively charged, E+, or it can be neutral, but it has got deficiency of electrons as a result of the fact that the atom to which it is bonded to, the more electronegative element, has taken most of the electrons away from it, making it electron deficient. The other type of electrophiles are those that have an incomplete octet, as we have seen. So the nucleophiles, they can be neutral or negatively charged. These are the ones that have lone pair of electrons. Okay, so water, for example, alcohol or amines, these are nucleophiles because they have this lone pair of electrons which they can donate. So they have this lone pair of electrons. Further, the bonds in which they are involved with is a polarized bond. Says that like this oxygen is bonded to hydrogen, which is less electronegative. So most of the electrons of the bond, the hydrogen oxygen bond, most of the electrons of this hydrogen oxygen bond are on the oxygen. So the oxygen is electron rich. Okay, so it uses its lone pair of electrons to form a bond with an electron acceptor, an electrophile. Okay, so the arrows are going to start from the lone pair of electrons. This is where the electrons are. Okay, this is where the electrons are. So the arrow will start from the lone pair of electrons, be it on neutral or negatively charged nucleophiles that have lone pair of electrons. The arrow will not start from the negative charge, from this minus. The arrow starts from the lone pair of electrons, from here or from here. This is where the electrons are. Okay, so the tail of the arrow will be on this lone pair of electrons and points towards the electrophile. In the case of a pi bond, the electrons are not on a lone pair, but the electrons are found between the two carbons. Okay, so if you look at this has got sigma bond and pi bond. Okay, so the sigma bonds in here are not accessible, but the pi bonds are accessible, and then these pi bonds, the electrons of the pi bond, are between the two atoms. So when you use an alkene or a compound that has got a pi bond between identical elements, a non-polar pi bond, the arrow, the tail, will start from the middle and it points towards the electrophile. Okay, so it is very precise. You cannot start an arrow from an atom like this. Okay, you cannot start it from here. You cannot even start from the nitrogen, or in here you cannot start it from the negative charge. The arrow should start from the lone pair of electrons in this case. Okay, that's where the electrons are, the excess electrons that are there to be donated. Okay, so in the case of a pi bond, the electrons are between the two atoms. So that's where we start. Then after that, starting from here, the arrow will point towards the head where the electrophiles are. And the electrophiles, as we said, they are you can have positively charged electrophiles or neutral electrophiles that have partial positive charge. So this is a neutral molecule because of the polarization of the bond. This carbon is electrophilic, this one is also electrophilic, this one is electrophilic. So the electrons that are going to be donated by the nucleophile will land on this carbon, from here to this carbon, from here to that carbon, from here to the hydrogen, from here to this carbon, etc., from here to this nitrogen that is positively charged. Or they can also be because of such atoms that have got incomplete octets. So from here to the boron, from here to the aluminum, from the lone pair of electrons to the aluminum. Okay, so the arrows shows the movement of electrons. They do not show the movement of atoms. Atoms do not move. The only thing that move during a chemical reaction are electrons. For example, if you react this amine with this alkyl halide, So this is electron rich, this is a nucleophile, and this is an electrophile. You are going to show an arrow that starts from the lone pair of electrons ending up on the carbon. So these electrons, this lone pair of electrons, will be used to form a bond with this carbon. So there's going to be a bond that's going to be formed between the nitrogen and the carbon. Okay, so when that happens, the rest of the atom, including the nitrogen and this hydrogen, these different groups, they also move with it. Okay, so we don't show per se the movement of atoms, but the atoms move together with the electrons. Okay, so the arrow, the head of the arrow will point towards the electrophilic carbons, like this, to the atoms. Okay, to the atoms, to this atom, to this hydrogen, to this nitrogen, to this carbon, and forms a bond with it. Okay, so the head of the curved arrow always points to an atom. Okay, this is what we saw, from here to this, from here to this, from here to this, or they can also point on a bond. Okay, later I do not have an example as of now to show you how the head of the arrow points towards a bond. Later on, when we see the formation of a double bond, we'll see how the head of the arrow end up being pointing towards a bond. So the head of the curved arrow points to an atom or to a bond. Okay, so these are how this is the way curved arrows should be used precisely. Do not make a mistake of pointing an arrow from an electrophile to a nucleophile. It cannot happen. It's okay. So now you have a clear understanding of what a polar reaction is, what nucleophiles are, what electrophiles are, and how we should use a curved arrow. Then we'll put all this together and use it in proposing or elucidating the mechanism of polar reactions. Okay, so I will start with a simple example. Okay, and then I will once we know how to use the things we have learned in elucidating the mechanism of a simple reaction, then I will show you another example which is a bit more complicated, and then at the end of the day you'll have all the skills that are required to understand and elucidate the mechanism of an organic reaction. Understanding of reaction mechanism is very, 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 very important. Okay, for organic chemists, for chemists, as well as even biologists or geologists. Okay, any of us who are interested in life processes, we must understand organic reaction mechanisms. For example, in our body there are a lot of chemical reactions that happen. Okay, ATP hydrolyzing to give us energy, how ATP hydrolyzes to give energy, how carbohydrates metabolize to give energy, how fats metabolize to give us energy, etc. All these processes in biological system, you can understand them very well if you understand the basic principle how chemical reaction happen. Okay, so understanding reaction mechanism is very, very important, and it is not a very difficult concept per se, but at the end of the day, to understand, to have this concept at your fingertip, you need to exercise, you need to read, you need to use the concept in solving real actual problems of reaction mechanisms. Okay, so we'll look at examples.